when we're looking at a ramp, there's a lot of things that are going on. And the first thing we have to remember is that gravity always pulls down toward the center of the Earth. And we're going to rotate our axes as that's happening because we're on an angle. And so while we can determine what's happening with gravity, we need to break that into what's happening against the surface. We call that FG in the Y direction. And then what's happening parallel to the surface. And I'm drawing it in two places so we can see how the triangle works. But we'll have force of gravity in the X direction. The angle of the ramp is the same angle as the perpendicular is to gravity. And that will allow us to have a right triangle. The y is the adjacent side, so it's the cosine. So the force of gravity in the y direction is the force of gravity times the cosine of theta. Now the opposite side is our fg of x, and it's f of g times sine theta. But because of the way that we want to represent it on the box, we usually write it up at, like, stemming from the center of the box. So the fg of x is equal to the force of gravity times sine theta. And keeping in mind that the force of gravity is m times g, that's why the other ones are written there also. Force of friction goes against fg of x, and the normal force goes against fg of y. And if we're talking about a situation where we have no net force, then we'll have our fg of x will equal our force of friction, because if f net is equal to 0, those two numbers need to be equal. Let's say we have a mass of 12 kilograms on an inclined plane of 32 degrees. And so f of g is mass times gravity, so 12.0 kilograms times 9.81 meters per second squared. And that will give us a force of gravity of 118 newtons. Now we need to break that up into what's happening in the x and the y directions. And so we can draw those on there. Here's our fg of y. It's going against the surface. And that will be equal to the 118 times the cosine of theta. So 118 newtons times the cosine of 32. And when we do that, it gives us 100 newtons. We'll keep a couple of sig figs there, so 100 newtons. And then we do the same thing in the x direction. Fg in the x direction is equal to force of gravity times sine theta. So we'll take our 118 newtons times the sine of 32 degrees. When we do that, we end up with 63 newtons. And that's how gravity is affecting the box down the ramp. There's a couple other things going on here where we also have friction going back. Now, if we don't have any net force here, which is what we're going to assume, is our force of friction ends up being 63 newtons. And then also our normal force is going to be 100 newtons. If we're in a situation like this where net force is equal to 0 and we're looking for the coefficient of friction that's happening between those two surfaces, we know that our coefficient of friction is equal to our force of friction over our normal force. Our force of friction is Fg sine theta, and our normal force is F of G cosine theta. And those cancel out, and sine theta over cosine theta gives us tangent theta. So in this situation, we can do this because our net force equals 0. Now we're going to look at one where we have a slipperier slope. In this case, our mu is going to be 0.25. And we're going to put our force of gravity down there going down. And we'll break that into our x and our y as we're doing that. Our force of gravity is same mass, so it's still 118 newtons. When we go into our y is still 100 newtons. And when we go into our fg of x is still 63 newtons pulling down. In this situation, we are going to we don't have anything else added to it, so our normal force is going to be equal to the force of gravity in the y direction at 100 newtons. And then we're going to need to use our equation and our coefficient of friction in order to figure out our force of gravity, or our force of friction. So our force of friction is equal to mu times our normal force, so 0.25 times 100, which gives us a force of 25 newtons in the way of friction. Now we can figure out what's going on in the way of our acceleration overall. Because we know that our F net is always equal to our Fg of x going down the ramp minus our force of friction that's going against the motion. And because of that, we're able to make some sense of what's going on here. We know our Fg of x ends up being 63 newtons. We know our force of friction is 25 newtons, so we can get our net force equaling 38 newtons here. And because we know also that F equals ma, our 38 newtons is our net force here. So we can say that F equals ma, so 38 newtons is equal to 12 kilograms times our acceleration. When we divide both sides by our 12 kilograms, cancel out, and we get a is equal to 3.2 meters per second squared. Keep in mind that newtons equals kilograms times meters per second squared, which allows us to cancel out the kilograms. This equation is real important here, where we're looking at the way that F net and Fg of x and F of f relate. Because your net force is always going to be what's happening down the ramp in the x direction minus what's happening with the friction. And this can be broken up into different pieces. The thing that happens is, depending on what you have and depending on what you know, can become really important in how you approach the rest of the problem. So keeping that relationship in mind when there is acceleration that is being something that you're solving for, or some part of what's going on, that relationship becomes important in helping to solve it.